I welcome you to this section. I'm glad to have you here. My name is Topman Paul-Dike, and we'll be talking about linked list. We've had several sections where we did several things that are basic, and in some of these sections we had to rewind and go back to certain concepts like pointers, um, dynamic memory, like knowing that we have this kind of memory called dynamic memory, and of course other types like static memory, heap memory, you know, yeah. And then these are concepts that one should know to understand linked lists very well. Okay, and then recursion as well, of course, recursion. So it's got that in AX as we progress. I mean that we journey along a path of increasing complexity, and it's so much fun. It's so much fun when you pay attention to the bits. When you don't pay attention to certain things that are prerequisite or you should know, as you make progress, it gets more complex and it becomes confusing. So a lot of the times, what you need is to go back and pay attention to something you didn't give enough attention. All right. So, but I want to save time in this section, so I wouldn't be talking about these things now. You can find them in other of my videos. But for now, I will go straight into linked list. What is a linked list? A linked list is a kind of structure. I've demonstrated this before in in the first one too. Yeah, there is this kind of structure. The first video I did about or the first video of this series, rather. Okay. Okay, let's say we have a list like this. I mean, an array representation of a similar thing will look like this, where we have an array of size 4. Okay, so this a linked list, like they call it, is a link, actually a link of several nodes. So when we say linked list, it's actually these things we are referring to. We are linking these stuffs together, this one to this one, this to this one. Having a head. Let me represent the head with this. Have a head, which is a pointer, actually. A pointer, yeah. A pointer in itself. Why this one is a struct? These ones are structs. They are called nodes. Nodes. And the structure or the what now? The construction that a node has in single list is 2 spaces, one for pointer and the other one for the data. Okay, so each of these nodes will look like this. Each of these nodes will look like this, and one part of it will be holding data, another part will be holding the pointer. What is a pointer? Remember, a pointer stores the value of the memory address. Yeah, the value of the memory of a particular variable, or let me say thing, because pointers can actually hold, I mean, the functions can actually be stored in variables, right? So pointers are variables that store the memory address of a variable. What do you mean by that? I've explained this several times, but let me just do a little one. It's like let's say in an estate where there are plenty of houses here, plenty of houses, several houses. Let's say there's a man named Frederick. Let's say Frederick. I'll put F for Frederick. And one lives somewhere around here, but the estate has a gate, and you agree with me that it is most likely that the person here will have the address of everybody. So if you go to this man and say you're looking for this person, so long as he's aware that this person is coming and that this person is not a criminal or is not, I mean, for security reasons, he has to be aware that this person is coming. He has your address. You can tell the person, take this route and go straight. You will see a house at the edge. That is Mr. Frederick's house. Right. So because pointer has the capacity to store the memory address of variables, they can also access what is inside that variable. Right. Remember, variables are containers. Right. So I'm going to be using variables of type int in these illustrations. So linked list, you will see pointers everywhere. You know, this node is actually a self-referential structure. I will explain that when we'll get into the coding section. So let me talk about linked list operations and then the types of linked lists. Right. So an array is arranged like this in memory such that if you know the address of this one, if it's an array of integers, for example, if you know the address of this one, if you add 4 to the address of this one, you will get the address of this one. If you add 4 to the address of this one, you get this one. If you add 4 to the address of this one, you get the address of this one, because the name of the array itself is a pointer to the member or element at index 0. And I don't want to rely so much on these ones. I want to focus on single linked lists. So let's talk about types of linked list first. So I'm going to take this off. Types of linked lists. So we have a single linked list, we have a doubly linked list, and we have a circular. Now, why arrays are arranged in a sequential order, linked lists are not actually sequential. That means you can have this one somewhere here and have this one somewhere here, but they'll be linked. They'll be all linked together, so that the head will be linked. Maybe this one will be the first one, and this one now will not have a pointer here that is pointing to. Let's say this one is the second one. It will not have a pointer here that has the address of. Let's say this one is the third one, and this one will not have a pointer here that has the address of the last one, and the last one will not be pointing to null. Right? Okay, but just for easy understanding, that's why you're putting it straight. It never occurs like this in memory. Okay. So what's the difference between single linked list, double linked list, and circular linked list? Let me talk a bit about the operations before I talk about the difference between these types. Okay, so the operations that you can see in single linked lists. Why is this guy suddenly big? Oh, it's another one. Okay, my board is getting rough. So operations, or let me say linked list operations. It's getting interesting, right? So I'll call it linked list operations. Okay. Having known that it's a linking of nodes together, right? Then it becomes obvious that a technique has to be followed. So it wouldn't sound too exoteric to use the word inserting. We'll say inserting. So inserting means inserting a node. A node. It could be inserting it. Let's assume that these guys are linked together right now. So this one is linked to this one. This one linked to this one. this one links to this one, and this one links to this one. So what if I want to insert a node here? If I want to insert a node here in between this one, I don't want the node to be the last one. So just the insertion is act of adding a new node at a particular position, at a position of interest. I could add it at the beginning here. I could add it in between nodes. I could add it at the end. So inserting at the beginning, inserting at the end, inserting anywhere. Just know that's insertion. That's what insertion is. Insertion, simply inserting, adding to it. So adding to this, we um, go through a process like this where we have a node. We create a node first, give it its data, and then we'll now come here and move this node. Right? How do we move it? We make the pointer of this one. We make the pointer of this one. It should be pointing to null actually. We will now make the pointer of this one to point to this place. And we'll make the pointer of this one to stop holding the address of this one. It will now start holding the address of this particular one. So once you do that, you will have something like this. Let me wipe this. You have something like this, where this one is no more pointing to this place, but now pointing to this particular one, right? And then this one now is not the one pointing to this one. So it means this one is holding the address. This pointer here is holding the address of this one, and the pointer here is holding the address of this one. Okay, and then at the end of the day, you're going to have a structure that looks like this, where this guy moves. This guy will now move like this. This is just some pictorial representation of something. I mean, it doesn't really exist like this. And then at the end of the day, we have our linked lists. Yeah, this is the node, and then we'll have the pointer here accurately holding the memory of address of this one, and this one holding the memory of address of this one, and this one pointing to null, null, nothing. Right? Okay. Another time I'd like to talk about God has got to be more effective than this. Just the way you can insert, you can actually delete as well. So let me say deleting. Of course, you can. I mean, you can. If I let you try, if I ask you to meet and talk now, or try to explain, I believe you'll be able to explain or give or make attempts, right? So deleting take almost the same thing. You want to remove this one. As you're removing it, make sure that the pointer of the one that was before it is not pointing to the one that is next to it. That's all you need to do. Stop pointing to this one and point to this one. That way you have removed this one. Even if it still exists, you have removed it from the list. It's no more in the list. Right? Or yeah, it's no more in the link. It's no more in the link, rather. I think that's a better way of saying it. Okay. Okay, this operation are basic, right? I mean, there could be more. There could be more. So I will talk about just two more. One, I will talk about searching, and then I will talk about transversal, which is transversing, which is very important because I mean you couldn't just this thing that we did here, adding the node. We need to move from here to here. For example, we know that this is the here, this is the first node, second node, third node. We added that node between the third and fourth node, and that node became the fourth node. So we will have to transverse, move from the head, for the head pointer, to this one, to this one, to this one, until we get to where we want to add the node. That's what we call transversing. That movement, assessing each node one after the other until you get to the node of interest. Right? So it's a technique that could be used in inserting, it could be used in deleting, it could be used in searching as well. Of course, searching is literal. You're searching for a particular value, right? Because these nodes will hold values, they will hold data. Okay, having talked about that. I think I can now talk about the difference between the three types of lists: the singly linked list and the so let me see, let me add linked here, or let me add linked lists like that. Linked list. So I'll copy this, paste here, and paste here. The singly linked list is just like this. What I'm saying here. So you're saying here, the transversal can only be one way. Movement can only be forward. You can't move backward. You move from the beginning to the end. You can't move from end to the beginning. You move from node 1 to node 2. You can't move from node 2 to node 1. So it's only forward movement. Whereas the doubly linked list will look something like this, where we have two of these. We have the head pointer and the tail pointer. So one at the end here. So this guy will not be pointing to null again. It's not be pointing to null again. It will be pointing to oh, it's not be pointing to this one. Now, the interesting thing to note is that the structure of the node now changes such that it now has two pointers. This is what double linked list look like. It now has two pointers. Right? What you're discussing in this section is basic. It's really basic. So because it has two pointers, this particular one will be pointing to the previous one. This particular one will be pointing to the next one. That means this guy has the address of this guy, and this guy, let me use another color here. This one also has the address of this one. This one has the address of this one. This one also has the address of this one. Meanwhile, the data is saved in the middle. Let me use D to denote data. So data, I use the word middle because like that's the pictorial view we have in our imagination about this, right? So data will be here. This one now will be holding the address of this one. This one will be holding the address of this one. This one will be holding the address of this one, and this one as well. This one as well will be holding the address of this one. So it now it's almost looking like he has two heads, right? Nonetheless, we still refer to one as head. I mean, at least you have a beginning now at the end, and refer to the other one as the tail. So this makes movement possible, forward and backward, where the list can move forward and move backward. So transversal can happen this way. Okay. So that way, if you want to insert something at the tail, I mean, this is a kind of abstract data type, right? Okay, I explained all of those in the part 1. Okay, so I think with this, I think that's enough knowledge. So that's enough knowledge to go into coding. We've compared, I've compared linked lists and arrays in some of those videos. Now, as for which one is best, they can't replace one another. They are different from one another. The cost of performing certain actions, certain operations in both of them may have different time complexity and even different space complexity. So one may be more efficient than the other, depending on what you want to do with them. So you want to choose, you make a choice based on your knowledge of how they function, how they work, how easy it is to work with them. And that's where that scary time, big O notation comes to play. Big O notation. Where let's not go into that for now. I think that's a topic that will make us discuss that in the details. So now let's try to do some code. Let's try to form a list. I'm going to put a picture of the list I want us to form, and then we'll go ahead and form it. So let me Let me copy this. No, I just go into a new board. So this will be an example. Example. I'm thinking now. Let's make a list of the age of, let's say, of 5 classmates. So this classmate, there are 5 of them, and want to store their ages in a linked list. Okay. Uh, let's say the age or the ages of 5 classmates. In, okay. Let me put it like a question. Store the ages of 5 classmates in a singly linked list. Let's give those ages. One is age. So let me now maybe make construct the sentence in better. Store the following ages of 5 classmates in a single linked list. So the first one will be 15. Second one is 12. The third one is 13. The fourth one is 16. And the fifth one is the youngest. So young. 11. Okay, one of the studies using a single linked list. I mean, if you wanted to do that using array, I want to believe you can handle that. So I'm gonna make this large, reducing a bit, and let's roll. So I would like to see the into. There's this repository where I push the codes right from the journey through C to do what to create a visit. It's called journey through C. So this is where I push codes that write in these sections. Okay, and we've done single linked lists several times. And some of them we have put, I think 2 times on 2 occasions we pushed to this place. Yeah, interesting, quite interesting. And the readme is such that some of the readme is such that you will understand, have a good understanding of what we had. Doesn't have a readme. It doesn't have a readme. That's interesting. I know we talked about struct. You see here, and the readme alone, I took my time to write it such that you can read and even learn from it. It was so illustrative. Okay, I just want to show you that. That's by the way. Now let's do some coding. I am going to find that repository here. I want to believe I have it here. Okay, there it is. Journey through C. I'm going to move into the repository where we push the formal code. So 9 single place. I'm going to make I'm going to make a new directory. Single linked list. Just for us to do some more work. Let me be sure that this repository is up to date. Shall we get pull? Wow, he wasn't up to date actually. Clear my screen. So we don't have anything inside. I'm not yet inside. We don't have anything inside this directory yet. So I'm going to create 2 files. So I'll call this one student age or classmates age. Classmates ages. dot c. I'll do another one using array dot c, so that you appreciate what you want to achieve using this single list. Let's start from the known to the unknown. So we're going to begin with the array. Let's achieve that with an array. Of course, you know that our program will begin with this kind because we are going to have it printed in the standard output. So stdio.h. Okay, so int main void, and here we go. I'm going to close it first. Oh, I'm going to have a return value. Okay, so now the edges again. Let's make copy the edges and put them as a comment here. Can I copy this in like this? Okay, so 15, 12, 13, 16, 11, 15, 12, 13, 16, 11, 1, 2, 3, 4, 5. Okay, I believe it's correct. Of course, the standard way to write a single line comment is this way, as we were taught. Okay, to do this using an array, we're going to have something like this. Here we declare the array int ages, and when I say ages is an array of size 5, when I say it is equal to these numbers 15, 12, 13, 16. I'm assuming that you know something about arrays. So this for me is moving from the known to the unknown. Okay, especially if you're an LS student. By now, I mean, before you talk about linked lists, you should know something about arrays. You should have learned about arrays. You should have written functions, that does something to arrays. Okay, so how do we print this stuff out? If I decide to do this, print f, I say print for me, percentage I, so percentage I, and then lose this, and then name of. See what happens when I do this. So let me save this and minimize and try to complete. So using C, I will save the output as array if it will work. So it wouldn't work. It wouldn't work. So you want to look through those elements, look through all of those elements, and I'm going to use a for loop to do that. So for it says it's a wrong practice to declare a variable inside the for loop, so I'll go and declare it here. So int index, right? So for index, this is us initializing it, giving it an initial value, right? For index equal to 0, as long as index is less than 5, which is the size of that array. I mean, this is 0, 1, 2, 3, 4. Remember, we come from 0, 0, 1, 2, 3, 4. So that's how it is indexed. Okay, so we don't have to get to 5 to access this guy. This guy is 4. So ages of 0 is this. Ages square bracket 1 is this. Let's go ahead. So as long as index is less than 5, keep incrementing index. And what you do, okay, it's a good practice to put this curly brace, although you don't need it when the instruction in the for loop is just one line of code. So give me a jigs index. Why do I have index in square brackets? When index is 0, this will be age 0. And I want to believe that you know that age 0 will be referring to the first member of this array. which is 15. All right. So it keeps increasing from 1 to 2 to 3 to 4, and all these numbers will be printed out. Then after printing them out, in fact, I need a space here. After printing them all out, I want it to come out of the loop and print a new line. Let me use bootcut this time. Print a new line. Okay, let's see. There's no syntax error or bug in this program. It should be one. So I'm going to try to compile again. So it compiled, no error this time. Let's run it now. So we have 15, 12, 13, 16, 11. Now let's do the same thing using a linked list, right? I'm going to copy what I have here so I don't start including how the basic structure. I'm going to copy it into the file. What's that file again? Classmates edges. Let's see. Okay, so I will exit this editor and open classmates edges, and then I will remove what I don't want. I don't want this again. I don't want this for now. Let's do like this. All right, these are the edges of the classmates I want to print. I want to store in a linked list structure. First, you've got to know about something called struct. Something called struct. A functionality in C that allows us to define data types that are not in existence by default. So we can define our own data types. In fact, I could say that, okay, let's not just have only their ages, let's have even their names. Let's have more information about them. So it prints this person's name. For example, if this one is John, it prints John and print 15. It will save. The next one will save. I mean, we even did one. Okay, it was here, right? We had to construct a structure that saves phone number, right? Like for contact. Want to control some data type like that. So that's the capacity, the enablements that you get from using struct. Let's see. So how do we use struct now? If you go struct, the keyword struct, because we have to define the struct globally, right? Globally in the sense that we're not doing it inside a block of code. We are coming out of the block of code and it makes it available to every other thing that is down here. Okay, so we go struct, now give it the name that I want to give it. Usually you will see struct node, but it could be what you choose to call it. It could be what you choose to call it. So let's call it struct age. Struct age. Yeah, age. Or let's say, okay, my node. I just don't want to have something you see everywhere, so that you don't have the mentality of it must be called node, right? When you do this, next thing you want to do is define what you want to be there. We want a data type of int, and that data type, data or that variable age should store age. We also want a pointer inside. This is the point where I say it is self-referential structure. We want a pointer of type struct my node. I will try to explain what that means shortly. So we'll call it like to call it some like to call it nest. I just want to do something unconventional, something not usual, something not rampant. You can suggest a name for me, I don't mind. Nest. Oh, maybe I should use the nest. Just know that you can call it anything, right? You can call it anything. But I just want to do something that makes sense. Okay, something that communicates it. Okay, next, we are good with this. I think we are good. But for Betty's sake, you don't want to leave this first curly brace on this line. You want to take it down like this. So this way we have our struct defined. Yeah, our struct defined like this. Let's go and find out whether it's working first. So let's declare a variable of type of this type. Let's say struct my node. Call the variable name testing. I just call it testing. I want to test and see. But it's important that you allocate memory to it by yourself. And to do that, we'll need the library. What happened here? No, I don't need you. We'll need the library stdlib.h. We need that header file here. And then we'll now use the malloc function. So after declaring this variable here, I want to, okay, so let's see what testing can save. Malloc, I hope I'm not doing this wrongly. Malloc, the size, of course, you are saving this, you are allocating this size to testing. No. If it was a point, I would have done this. Let's do testing.age equals, let's see, 15. And testing.next is equal to null. Okay, if this works, printf should be able to locate it. Printf, because it's an integer, we use this format specifier, and then say print for us the value of testing dot age and a new line after that. So let's see whether this is okay and working. Let's see whether it will compile without error. Let me clear the screen a bit. All right, so GCC classmate ages output is to testing or refuse. Oh, what did I call it? Okay. Field next has incomplete type. Struct my node next. Oh, it's supposed to be a pointer. Okay. Let's see now. So it compiled this time. So if I run the file, let's see what happens. It prints 15. That means it's working. It's working. Now let's make progress. Okay, so we want to create that first guy head, right? Let's go and do some whiteboarding. Let's go and try to solve the problem on the whiteboard. So we want to create something like this. Now we'll have our head pointer, and then we'll have 5 nodes. I hope this is what it really looks like. I hope I'm not making some mistake, because there's been this argument whether the head pointer is part of it, or whether it's the first node or what. Well, that's not my area of concern now. My concern is that you should understand what linked list is and how it works. All right. So we want to go and create this kind of thing. We're trying to make a pictorial representation of what we want to go and achieve with codes. I think I'll delete these ones and take same size. Node 2, node 3, node 4, node 5. So I would want to have this kind of structure. Let's call this node 1 for the first student, node 2, 3, 4, and 5. Okay, and this will be the head. Uh-oh. I'm actually using my mouse, pardon me. All right. Now what we actually want was to have the address of this guy saved here. Right? And the address of this one saved here. And the address of this one saved here. And the address of this one, this node, saved here. And the address of this one saved here. This here that I'm referring to, this thing that I'm calling here is actually the nest on our struct node there. Nest. Right? That's a nest instead of structure. Okay. And okay. Making progress. So we want to have 15 as the data here. We also want to have 12 here on the second node. We want to have 13 here. We want to have 16 here. And we want to have 11 here. And of course, we're going to be having null here. It's going to be pointing to null. So let me complete this diagram. The address to null will be saved here. Address to nothing will be saved here. Okay. So we want to achieve this kind of structure, right? Now this represents what we want to achieve, our final goal. And I will try to replicate the diagram as we make progress. Let's start achieving them one by one. All right. I wish I could change the color of this second this thing. Want to achieve them one by one. So let's go and make the head. The head has to be a pointer, right? Because it's saving the address of something. So let's go and have a head pointer here. And so I'm taking this off. I will take this off for now. Take this off for now. Oh, we actually need it later, so let me leave it there. So this has to be a pointer. I will change this name. I will call it head. It could be named anything. I'll call it head because it means head pointer. Head pointer. But let me say head PTR. Head pointer. Okay. I want to allocate some memory to it. So head PTR. I want to save the return value of this function I'm calling here right now. So malloc the size of, that means allocate dynamically the size of struct node, struct my node, right? Allocate it, to head pointer. All right. So when we do this, let me comment this side off. By doing this, we already have a head pointer, right? Let me also comment this code. Write the code. We already have a node pointer because we've created a space in memory. A space has been dynamically allocated to it, to head pointer. So head pointer now has the capacity to store the address of node 1. Let's continue now. Now, having had this first head pointer, we can now allocate the memory, put the data that we want. So okay, head pointer dot age is equal to 15. The head pointer dot next equals node. So head pointer has been created and we have the first node. That's what that code means. We already have the first node. So we have created this. All right, and inside there we'll have 15. So let me do this. We have 15 here. And this is pointing to null. Okay, I think this color should be another color. Let's make it black or the same blue to demarcate this from this. So we already have something like this. Okay. Yeah, that's it. I think it is because head pointer is holding some address dynamically allocated to it, and that address, so that memory space is for the first node, and the first node has been created. I think it's so. You can inform me if you think it's not so. Now we have this right now, right? Now let's go ahead. How do we now create this other one? How do we now have this other one? Let's have another pointer called next here. So we'll create 2 pointers of this same data type. So here will be let's call this one next pointer. Next pointer. And we'll come here and now allocate a new memory. I think I'm going to copy what I have here and try to place it down here. So this time it will be next pointer, or should I call it next node? Let's leave it as next pointer. Okay, so we have allocated memory to next pointer, right? We want to form the next node. We'll now say next pointer dot. When we say dot, we are accessing the should I say child, the content inside it, this part of it, the subdivision of it called age, and we are putting the value of 12 into it, the age of the second student, and we now make this one ptr dot next should now be the one pointing to null. So by doing this, what we have now is something like this. We now have a second node, right? And this second node has the value of this is not pointing to null. Okay, let me do it like this. This and this is now pointing to the same thing, to the same null. but this has 12. Yeah, this is what we have. So they're not really linked together right now. We need to link them. How do we link them? By having the value of this one stored here. Okay, that's how we link them. So to do that, we'll add one more line of code here and say this guy at line 19 that was initially pointing to nothing will now point dot next. We now point to this particular pointer next ptr. Okay, that's it. That's it. So you can see now that it is now that next. That by doing this, what we did was this. We're not saying that this particular space here should not be pointing to this place, such that it's not be pointing to null again. It was pointing to null before, but it is no more pointing to null now. We have successfully linked it with this one. Right? Right? So let's bring it closer. We've achieved this. We've achieved this. We've achieved this linking. It's been successfully linked together. I'm going to write the value here. So we have 12. And we have our pointer here pointing to null. Let me wipe this off. You're making progress, right? Okay. So this is now, where's my pointer? My cursor. This is now pointing to null. This is what we have here now in our code. This is what we have here. So it's cool. So the head pointer has what? See when we say head pointer is equal to this, and head pointer is having the memory of this guy is the first node, and the first node now, the next that the pointer that this pointer next that is inside the next node is now having the address of next pointer. Okay, next pointer. So in doing that, it's more like it's looking like I think it looks more like we created another pointer, right? Named. Follow this logic closely, please. Start to look complex now. Why this one is named head ptr I'm gonna get this small. This is what it looks like more. We have another pointer here named yeah, I think this is more like it. We have another pointer here named next ptr. We use this pointer actually to fix this guy here. That's what it looks like, because at that point the pointer had the address of this guy. When we did malloc to this pointer, when we did malloc to this head pointer, it now had the address that the dynamically allocated address of this guy. It now had it. We now use it to put into it what want to be there in that node. We now declared another pointer and have it stored at the address dynamically of this node while the data was there to enter. The 12 was there to enter. So we now data put 12. So it means that even up to now, this next pointer still has the address of this guy. So I want to use the next pointer to form. I don't want to start creating plenty of pointers, right? I want to use the next pointer to create this other node. So I will go and free it from this guy, right? I'll not say, hello, sorry for the interruption. Confirm that you can hear me, please. Okay, sorry for the interruption. All right, so I want to use this head point, this same point that I've declared to go and do some more work here. Right, so I will come here, take this line, exactly this line the way it is, and declare it down here. So now the next pointer, now give it a new space, give it a new memory allocation. And what we want to do is this. So I will just copy these lines the way they are. So copy this line, paste it here, copy this other line as well, and paste it here. Okay. So let me take out this necessary line. So this time we're going for the next age, which is 13. This is now 13. All right. So what we've done by doing this, what we've done is this. Let's go. What I've done is to remove the value of this pointer from this one and give it the value of another pointer, as another node rather. I will remove the value of this node from this one and giving it a new value, a new memory allocation. So that one will now be this one I want to create. How? Let's demonstrate that. Let me demonstrate that. So we'll now have the third node created here, right? And of course, let me take this node somewhere down. So, man, I wish there was something better to use in this illustration that would make me put up diagrams faster. I guess like this faster. Okay, so I don't want to. Let's remember that this guy is still pointing to null. I'm taking it slowly so I don't end up confusing us, right? This guy is still pointing to null, right? So this guy, this one is here. I want to create this one. This guy now, I've said this guy stop pointing to this one. Come on now, come on, start pointing to this one now. Want to use it to fix it. So we have moved this pointer to this place now. It is now having the address of this guy. So that's what we have done. Next pointer now has the address of the next node, and we have put what's it called? We have put, because it has the address, we have put 13 into this place using this next pointer, and this other one is pointing to null as well. This side is now pointing to null. Let me maintain for consistency. Let me just use blue to divide the data from the pointer. Okay. At this point now, yeah, it's making more sense now. Now, no, the head pointer is not the first node. I say is the pointer to the first node. So now these two don't have any link yet. There's no link between this second node and the third node from our code yet. There's no link. To implement that, we have to make this guy point to this guy. How do we achieve that? How do we achieve that? But the question, how do we not achieve that? Because if you come here and say something like this, you will come and say, okay, okay. If I say next PTR, because we came here and say, okay, head now that was node is not equal to next PTR. If we now come here and say next PTR dot next is not equal to next PTR, there will be trouble. I think so. Because next PTR dot next is no more this, how do I put that? It's no more the second node. Next PTR dot next is no more referring to the second node, because at this point, next PTR has nothing to do with the second node again. It is not concerned with the third node which we just created. So next PTR will mean here. Next PTR dot next will mean this place. It will not mean this place. right? It was here, but when we did last malloc that we did, it now became here. Next put arrow.next will be this place. It's no more this place. So if we say here is equal to, I mean, there'll be some conflict. We'll be causing some problem. We don't want to cause some what is it called now? Like this, what do you call this? Um, as this term when you are accessing an illegal memory, as this natural security mechanism. If anybody is nobody is talking, I'm the only one talking yet. No problem. Okay. Next. So what do? We now use that guy, use the head pointer to access it. How? At this point, I think I want to use the okay, let's do it like this. Next PT, I'll now go to the head PTR. Head PTR. Head PTR.next is here. This is the head PTR, right? So to .next to be here. And .next is saving this place. Right? .PTR.next is the first node, and it's saving the address of the place. We want to catch the second node. The .next of the second node. So this whole guy represents the first node. This whole guy is like saying it's like having a code where we have something like we have a pointer here, PTR, which is equal to the address of n. Now PTR itself, this PTR now is representing this guy. Could represent this guy because we can use PTR to get the value that is here. So if n was a struct that has next, right? PTR.next will be able to catch this guy. So this guy is presenting the is it first node I said? Second node, second node, because second node is saved here. It's saved here. So that second node now, right? If all of this is representing the first node, sorry, the second node, rather, then the .next of the second node can be added here. And when I say it's not equal to this current next underscore PTR, I don't know whether that was clear enough, but let's check to see whether our code is correct by trying to print out the values in this place, and that will force us to transverse, to do transversal. So I will say okay, let's also column here, right? So I hope that's not confusing. So how do we now print out the values of these? Let me update our board. So when we say here is head PTR, here is head PTR.next. Let me do this. Okay, here is head PTR.next. We talked about this particular space here, right? So when we say .next, right, we are talking about this place. PTR.next. I feel like using the arrow. I hope this doesn't throw up any error. If it does, you will be forced to use the arrow. So we are not saying that this place should not hold the value of this place. By saying that, we have just said that this guy should stop pointing to null and start pointing to this node. So if that code has no bug in it, if there's no error in the syntax, and if there's no error in my logic and algorithm, then our code should work. Let's try to print out let's try to print out what we have now before I continue. Let's print out what we have. Okay, so to print it out, I need to transverse something that looks like looping. So I will say y head. Okay, y head dots. Sorry, y head ptr is not equal to. Sorry, is this okay? I don't believe it's not equal to no. What do I want you to do? I want you to print out the value. So print f percentage I space like this. What I want you to print is head ptr dot age, and when you do that, head no, I think I should start from here. I think I should take this off. I will explain that if it works. I want to say head ptr. New value of head ptr should not be equal to head ptr dot next. Okay, now I want to close this block of code. All right, let's see whether this works. Let's see whether this works. If there's no error in this code, okay, I'm seeing HED instead of HEAD. HED. Interesting, right? I just saved it. Okay, I want to have a new line here as well after this operating. So let us print a new line. Looks like a waste of printf. Didn't print as a new line. Saved. So let's try to compare and see. And the file is still classmate ages. So GCC classmate ages. I will see this one as what now? Linked list. Linked list. Or let's have the same name. So classmate ages. All right. Oh, there is trouble. Let's put it out of the malloc size of struct manode. What is the matter? Okay, it's preferring. I put it out as a pointer. Did you mean? Oh, the arrow notation. Wow. Okay. The first example was you use the dot instead of the arrow. It's okay. Let's use the arrow. Yes, it's necessary because this is a pointer. So it will want to use the arrow notation, and I think it's like this. I'm not sure. Someone can unmute and remind me. Is it like this? Is it like this? I think it's like this, the way it should. Okay, so let's use arrow or true. Okay, so let's try again. Okay, so I'm going to clear the screen. I'm going to call back that command and compile again. More errors. What's up? I have my struct node. Right, this is a pointer. Genuine user. Is there a dot somewhere? Oh, there's still some dots. Oh, okay. In my print F. And here. Any other one? I don't think so. Okay. Even some more here. Whoa. Quite interesting, right? Okay. Now let's save. And I'm going to clear this screen and try to run that command again. What's up? Sorry. Incompatible types when assigning to type struct or not from type word. Excuse me. Something is wrong somewhere and I've got to figure it out. This is time to fight. Oh wow, my nest is not a pointer. What a bug. It's not supposed to be a pointer. Okay. Okay. All right, let's see what that's the issue by trying to compile again. I'll clear the screen. Try compiling again. Oh, it compiled now. So that was the issue. That was the issue. All right. Once more, look at the that of array I prints. Let's look at that of that one achieved with this guy. You can see that I already have a list of 3 nodes holding 3 edges. So I can leave the rest for you. You go ahead and complete it. Okay, maybe we should complete it together. Let's complete it together. This time I'm going to make it easier by having a function do it for us, because writing functions is one thing you are going to do throughout the journey, in fact throughout your life, as long as you make it into the tech space, right? So let's make things easier by using functions. Okay, we can write a function that can create a node. We can write a function that can insert a new node. We can write a function that can do several things, but let's begin from, okay, I think I should stop here. I think I should stop here for now. This is enough. Next, in our next section, we have this code made easy. This plenty of code that we have here in our classmates pages.c. We'll make it easy by using functions. So these lines of code will be very much shorter. We have a function that will create the head node, and we'll have a function that will insert new node, and we'll keep inserting new node, we'll insert many nodes, so it becomes easier to insert the 5 nodes. I mean, we won't be having this kind of long thing here, right? We won't have need for this. And then we'll have a function that will print the list, the single linked list, what we have there. And then we have some more functions. Maybe one insert at the end, insert at the beginning, insert at a particular position, things like that, if we have enough time. So for now, any questions? There's no question. We might call it a day here.